Hello! So, in this video, I want to talk about these things called periodic solutions, and then we're going to link that to introduce this idea of this thing called limit cycles. And then finally, we're going to end up with a nice theorem, very scary sounding theorem, called the Poincare-Bendixon theorem, which sounds very scary, like I say, but it's actually just common sense. If you get these ideas in your head, it's just common sense. So again, we've got our what's known as our autonomous system of equations. By the way, autonomous, I don't think I've really talked about this word before. Autonomous, A-U-T-O, autonomous. Okay, autonomous, well, it kind of is linked to automatic. Okay, automatic is just kind of it takes care of itself. Okay, well, autonomous is very much the same thing. And it's just basically if you've got these kind of systems of equations, so dx by dt and dy by dt, remember these are just how our variables change over time, and they're both equal to some function. Well, if this function is dependent on t, so in other words, if we've got a function that is just dependent on time itself, then it's called non-autonomous. Okay, but if there's no t involved, then it means that it can just take care of itself. It doesn't matter about what time you're at. All right, so in that case, it's called autonomous. So if this right-hand side is dependent on t, if it's got a t in, then we call that non-autonomous. If it hasn't got a t in, it means it can take care of itself. It doesn't depend on kind of t in order to tell you what the value is, what time you're at to tell you what the value is. It takes care of itself, so therefore that's known as autonomous. So that's just a very quick kind of sideline. So again, we can combine these two ODEs, or however many ODEs we've got, into sort of one nice, neat little one equation kind of thing, to combine these two equations into one equation. I'm just writing it now, instead of having my vector notation or whatever, I'm just writing it as some function, all right, on the right-hand side. Now, the whole idea with periodic solutions is that we've got x, okay, so x vector now is all our variables contained, okay, and let's suppose that the x vector is dependent as a function of t plus... Okay, so let's now suppose that our x vector is dependent on not just t, but also on some time period. Okay, so on some small little time period which we move through. Okay, so in other words, it comes back to that same point, some other point in time, if that makes sense. If you think the most easiest example of a periodic function is the sine graph or the cos graph, because you sort of carry out one cycle and then you do the same thing again, then you do the same thing again. So all this t is telling us is it's just how many cycles you've been through. All right, so usually it's, with a sine function you go 0 to 2t, well then you come to the same point sort of every 2 pi, right? Sorry, did I say 2t? I meant 2 pi. Okay, so you come back to the same point every 2 pi. Okay, so this is 6 pi, etc., etc., etc. So you've gone through one cycle. It's just kind of this whole idea of a periodic function, and all this tau is telling us is just how many periods you've been through. Okay, so this kind of links into this idea of this thing called a periodic solution. So if you get this kind of idea in your head that it's just a solution which comes back to the same point again and again and again, and remember a solution can be drawn graphically. So what would it look like? Well, it just looks something like this. Okay. So it just looked like a circle. Sorry, that wasn't the best drawn circle in the world. Let's hope they meet up. There we go. So it's just a circle. So you just keep going round in this circle over and over again. Okay, so you end up in almost like this endless loop. Now, it couldn't always be a circle. That's just a general, that's just generally how we draw it. It could be anything you like. It could be any shape. The point is that you travel along that shape and you always come back to the same point. Okay, and you just keep on travelling along it as you travel in, kind of as you go forward in time. Okay, well... The thing is, periodic solutions often occur, okay, but so often we're just looking at values which are close to the equilibrium point. So in other words, we look at values close to the equilibrium point, and we may be given some initial conditions. So normally the initial conditions are given close to time 0, all right, because it's normally at the equilibrium point. So we just consider the initial conditions close to time 0. So x considered at t equals 0. Right, well that's just going to be x of 0, and we usually give that some value, and let's call it x0. Then the same thing for y, evaluated at time 0. That's we can write that simply as y of 0, yeah, because this is x of t and y of t, and that's normally evaluated at that's y 0 as well. So that's just another value. Okay, well normally close to the kind of beginning of our solutions, we're given this, what's known as initial conditions. All right, and the clue's kind of in the name. The initial part is towards the start. Okay, so we're considering right at the beginning of time, if you like, the birth of the universe or the birth of these solutions, right? Sorry, I shouldn't have said birth of the universe, it's probably confusing now, but birth of these solutions, all right? And normally what happens close to these, normally we get kind of cases which spiral in, you know, towards the equilibrium point, like this. That's not spiral, is it? You get the idea anyway. You know, they all basically head for this equilibrium point. You think, oh, well then that's true for the whole phase portrait. That's true for all points in time, that anywhere in this phase portrait, let me just draw in a set of axes, maybe that makes a little bit more sense, that anywhere in this kind of phase portrait, we can have all of the trajectories heading towards this point. But quite often, actually, we get these things called periodic solutions happening. So basically, as we consider points which are, or the trajectories which are slightly further away from the equilibrium point, what we end up with is that actually they end up in a periodic cycle. So we've got our equilibrium point, okay, and all the trajectories head in towards this equilibrium point. All right, but actually, as we consider points which are further away from this equilibrium point, we end up with what's known as a periodic solution, and this is just basically a cycle. Okay, we just keep going round and round and round and round and round. And this is true for points or trajectories which are further away from that equilibrium point. So close to that equilibrium point, the birth of that equilibrium point, if you like, all solutions, solutions which are close to this equilibrium point, head towards this this equilibrium point. But as we go further around, as we go further away, we end up going in a cycle. A nice way of visualizing this, remember I was talking in one video, or I may not have spoken about it in this sequence of videos, but I know that I've done a video talking about this basin of attractiveness, and I told you to think about a sink. So basically we've got this basin, and at the bottom of the basin, if you like, the plug hole is the equilibrium point, the point where all trajectories head in towards. So if you imagine now a marble or something on the side of this basin, it's going to obviously be falling in to this equilibrium point, right? Well, if you imagine it's now in 3D, okay, let me try and draw a 3D version of this sink. Okay, so you've got this basin of attractiveness sort of coming down like that, and you've got the equilibrium point in the middle. This is in 3D. I'm sorry, it's a terrible drawing. Maybe if we bulk it out a little bit. But anyway, you get the idea. But then basically on the side of the sink, all right, the edge of the sink, you end up with this cycle, this periodic solution. So as you head away from the sink, if you like, on the edge of the sink, it's usually, its curvature. Sorry, that's a terrible drawing. I'm not sure I can do much better. Hang on, let me pause the video and let me see if I can draw a better sink, all right? All right, maybe that might be a better drawing so you can see what's going on, okay? So basically, if we're inside this kind of, inside the sink, and if we're at any point inside the sink, we can basically drop a point in there, and it will always fall down towards this plug hole, and then kind of we're in the equilibrium point, okay? But if we're actually on the side of the sink, so on the edge of the sink, we're effectively in this limit cycle, so we can keep going round and round and round and round and round the sink, okay? And that's basically the idea which I want you to visualize with a kind of periodic solution. Sorry, I forgot the name of periodic solution. So inside the sink is, if you like, our initial conditions. That's kind of close to the equilibrium point. That's determined by our initial conditions. But then as we move further away, we basically end up with this periodic solution. Okay, and now we've got enough to talk about. Oh yeah, notice by the way as well that we get a periodic solution. Well, when does that happen? Well, when we do our eigenvalues, so lambda 1 and lambda 2, when they're purely imaginary. So they're purely imaginary. Okay, I'm not sure that's the right notation, but purely imaginary is basically what they mean, only. Okay, all right, I think that's enough now of that. So now I want to talk about these things called limit cycles, and it's kind of linked to this idea. Okay, the idea is that as you keep going out, so you've got this sink now, so close to the equilibrium point, given the initial conditions, that kind of close to time zero, everything falls towards the equilibrium point. But then as you go further away in time, as you carry on through time, you get this sink effect, so everything kind of gets in a cycle on the edge of the sink. But then as you go further and further out in time, you find that all solutions then tend towards the edge of the sink, okay? And they stay at the edge of the sink. They're not able to, if you like, get past the edge of the sink. It's almost like a barrier. Not able to get past the edge of the sink, and they end up in a limit cycle. So let me draw it in kind of 2D so that you can see a little better going on. So you've got my cycle. I've got my equilibrium point in the centre, okay, with my initial conditions telling me that I head towards or away. I could head away from the equilibrium point if it was kind of an upturn sink, all right? Yeah, anyway, here it was an upturned sink. Could head towards and away, but I'm just going to leave it towards for the moment. Okay, and then you've got the cycle. But then as you head further away in time, all solutions kind of trajectories come in, and basically, let me just try and draw this a little better. They basically get in this cycle. So they head in, and they basically end up getting in this cycle as well. Okay, so they come in from infinity, and they end up coming in, end up being in this cycle. All right. Now, can I picture an analogy? Well, yeah, kind of, I can. If you imagine in the sea, okay, you get these things called vortexes, which are effectively just eddy currents, okay, effective eddy currents. So you've got the sea, and you get these kind of vortexes which happen in the sea, okay, and this is exactly what this is. So you end up with like a vortex or a hurricane, you know, you could end up with a hurricane as well. Yeah, anyway, something like this. Okay, so basically as you come in closer and closer, so you come in, say, from the beach and you start swimming. Okay, you start swimming in this direction, keep swimming, or you come in this direction, keep swimming, or this direction, keep swimming. So you're basically coming in each direction. And what you basically end up with is you end up being sucked into this current. Okay, and you end up being sucked round and round and round and round and round. Likewise over here, or over here. You know, you end up coming in and you end up being again sucked round and round and round. So you come in basically, you swim towards it, you're not aware that the vortex is there, and you end up being sucked in and in and in and in. Well, if you're there at the beginning of the vortex, so in other words, close to the birth of this vortex, you know, I'm talking about the initial conditions in our case now. If you're there at the beginning, once the vortex is just starting up, you've got the centre, and then it's just starting to start up, so you may be sucked in. Okay, you may be ejected. I don't know if you can think of a case where it would be the other way around, where you're ejected. But this is the idea of a limit cycle. So in the limit, basically, as you're approaching, you know, a limit is basically when you're approaching some value. So in this case, you're approaching our vortex, or you're approaching our periodic solution. Okay. So you're approaching our periodic solution, and that's known as a limit. So you're approaching this value, and so this is why it's called a limit cycle, because in the limit you're getting in this cycle. You're approaching in the limit. You're approaching this situation here. You're approaching our vortex, and you're ending up in this cycle. Okay. So yeah, that's basically the idea of a limit cycle. You can have two different types of limit cycles, of course. You can have either a stable limit cycle. You can have an unstable limit cycle. These are fairly obvious. So stable, and you can have unstable case. These should be fairly intuitive if you kind of understand these ideas. So the stable case is where you've got your cycle. Okay, you're going round and round. You've got cycle in both cases. Going round and round and round. The stable case is where you're sucked in to this vortex, if you like, if you're sucked into this cycle. The unstable case is when you're thrown out of this cycle. All right, that's harder to think of real-world examples of unstable cases. Limit cycles, but you know it can happen. Okay, so these things are called limit cycles. Just think of a vortex. All right. Now I want to talk about. It's really good now. So now we've got these ideas. Now I want to talk about this idea of the existence. Okay, so to kind of come up with something that tells us whether a limit cycle actually exists. Okay, so there's kind of a few theorems. It's almost like a sequence of chronological order of steps that I needed to take you through before we end up where we want to be. Okay, so the first criterion, really, it's criterion. It's not really a theorem as such. You basically say, well, it's just a criterion because you're just given a list of criteria, and if these criteria are satisfied, then you've got some result. Okay, so the first one is the Dulac criterion. All right, and basically what you're given, right, is you're told that it has to, if you're given a simply connected region. So remember we were talking about domains and things before. This is just this is just exactly the same thing. It's just a domain. Okay, I'm just calling it a region. It's just like fencing an area of your graph, or whatever you want to consider your solutions, I suppose. You're fencing a region off, all right, and you're just considering that region. So that will give you what you want. Okay, and it's simply connected. Simply connected just basically... Well, let me talk about connected first, because simply connected is obviously just the next case on from connected. So if you've got a region, this is my region, all right, and if it's connected, it just basically means that you can choose 2 points in the region, and they will be connected by some path, all right, and you can travel along them both ways. Okay, if it's simply connected, it basically means there's no holes in this region. So, I mean, if it's just connected, then there could be a hole in this region, but that's okay because you're still able to find a path which almost, if you like, bypasses this hole. Okay, or could there be as many holes as you like, almost like Emmental cheese. Okay, you can pick any 2 points in a slice of Emmental cheese, all right, but you can always find a path between these 2 points. Yeah, because it's not completely separated like this. Okay, it's connected. Yeah, so you can pick 2 points and you can always find a path between them. If it's simply connected, it basically means that you've got no holes. So I don't know, it's a slice of cheddar, if you like. You know, you get rid of the holes and fill them in with whatever. So that's simply connected region. All right. You've still got your initial condition, or you've still got your initial, equations which we're used to now. So dx by dt and dy by dt, telling us how our variables change over time. Okay, and you've also got initial conditions. So I'm just setting up the basis of these. So you've got initial conditions, and these are just x at time 0 is just given as some value, and y at time 0 is given as another value. So you basically got what happens at the birth of your vortex, if you like. Okay, and once you've got those, then you basically suppose that there exists some scaling function. You're going to call this function b. All right, and what that basically means is it just scales your function to where you want it to be. All right, don't worry too much about it. Just accept that it exists. I think you can see why there should be a scaling function once you see an example. All right, so I'm not going to dwell too much on it. All you need to know is it's a scaling function. Okay, so it just basically makes our functions easier to deal with. All right, and basically, you suppose that you've got all these things. So you've got f and g. That's the most important parts, f and g, and this scaling function b. Once you've got these, then you can set up this. I don't know whether it's an equation or an expression, which goes like this. So the derivative of x so when you differentiate when you differentiate a scaling function b times f with respect to x, and you add it to the derivative with respect to y of our scaling function times g. Okay, so you differentiate our scaling function times g with respect to y, and you add the 2 things together. Then you need to then you've got 2 conditions that have to be met. So the first condition must be that it does not change sign within our region. Does not change sign in our region. So in other words, you've got our region here, all right, and you've set up this, so you work this out, okay, and you have to say, and basically if it doesn't change sign, all right, so with all the points in our region, if it doesn't change sign, that's the first condition that has to be met. And the second condition which has to be met is that it's not identically 0. So at every point, it can't be 0, 0, 0. No, it can't be 0, 0. So not 0 at every point. So it can be 0 at some points, but it can't be at every point. All right? And if these conditions are met, then that tells us that it's not a limit cycle. So a limit cycle does not exist. So if these 2 things are met, so say if that's met and that's met, so you work this out, and if you say, well, okay, I've got this, it doesn't change sign, and it's not 0 at every point, that's fine, then you kind of get a bit of a disappointment, I suppose. It's a bit like opening a shit present or a rubbish present at Christmas. It's a bit of a disappointment. So it tells you there's not a limit cycle. You think, oh, I wanted there to be a limit cycle, but it just tells you if these conditions are met, then there's definitely not a limit cycle. All right. Well, a bit of a stronger case, or no, not a stronger case, sorry, a bit of a more specific case is basically just a choice of this function here, and it's known as the Bendixon criterion. Bendixon criterion. So it's just a stronger case now of the Dulac criterion, and it's just basically choosing b equals 1. All right. And that's just a special case. So the best way of showing this is just through an example. So for example, if you've got dx by dt, okay, that's of course equal to f. And let's say it's equal to, let's say that f is equal to y effectively. And then we've also got dy by dt, and that's of course equal to g. And let's say this is equal to minus k squared y. All right. So we set up our thing which is defined in the Dulac criterion, so this thing here, okay. this thing here. So we want the derivative with respect to x of b times f plus the derivative with respect to y of b times g. All right, just that bracket in. So we've got d by dx of b times f. So b is just 1, f is y. So derivative with respect to x of y plus the derivative with respect to y. Again, b is 1. Okay, but now g is minus k squared y. So minus k squared y. All right, so derivative with respect to y of minus k squared y. So what's the derivative of y with respect to x? Well, it's 0. You just treat y as a constant, okay, because you're differentiating with respect to x. Plus, well, what's this? The derivative of minus k squared y with respect to y. It's going to be minus k squared. You happy? Because the y just differentiates to 1. You just treat minus k squared as a constant. So you're just left with minus k squared. Okay, so this is equal to minus k squared. Okay, so it's the same criterion as before. It can't change sign, and it mustn't be 0 at every single point. So we need to check this. Well, let's look at k squared. If you take a value and you square it, it's always going to be greater than or equal to 0. Because, of course, it can be equal, k can be equal to 0. All right, so if it's 0, you square it, it's still going to be 0. But otherwise, for every other value, it's always going to be some positive number. All right, because you square any number, it's going to become positive. But then look, you've got the minus. So that implies that minus k squared, so you've got a positive number or a 0 number, or a number which is equal to 0, and then you negate it. So therefore, that's always going to be less than or equal to 0. Yeah? Less than or equal to 0. Okay, so it's always going to be less than or equal to 0. So it doesn't change sign. So this does not change sign. That first condition is met. So it does not change sign. Okay, the next condition is that it can't be 0 at every single point in our region. Well, clearly it's only 0 at one point. Yeah, it's only 0 when k is actually equal to 0. At all other points, it's not equal to 0. It's always going to be negative. So it's not identically 0, or not 0 at every point. That condition is met. Okay, so these two conditions are met. So what does it tell us? There's not a limit cycle. Great. All right, okay. So there's definitely not a limit cycle. All right, that's okay. So it tells us there's not a limit cycle. But then you may be thinking that if these two conditions aren't met, then you might be thinking, well, does that mean there is a limit cycle? So say, for example, if it does change sign, then you may think, oh, well, okay, well, that means that there must be a limit cycle then, mustn't it? No, it doesn't mean that at all. It means that there could be a limit cycle. All right, so again, these are a bit of a rubbish, criterion. It tells us that there's not a limit cycle. Okay, great. So, yeah, we basically got a theorem or a criterion that tells us that there's not a limit cycle. Well, we really want, okay, and if these two criterions aren't satisfied, then they don't even tell us that there is a limit cycle. They just tell us that there might be a limit cycle. So there still might not be a limit cycle, okay? Just because these conditions aren't satisfied doesn't mean that there's definitely going to be a limit cycle, okay? So what we want is basically a theorem, a criterion, that gives us a limit cycle, okay, that we satisfied, that it gives us a limit cycle. Okay, and that's where this thing called the Poincaré Bendixon, so the same guy as before, Bendixon, teamed up with somebody and he made him see sense, if you like, and said, look, this really isn't good enough, is it? And said, you really need a theorem that shows that there is a limit cycle. And this is where the Poincaré-Bendixon theorem comes in, all right? It's a more powerful theorem, and it tells us that there's definitely going to be a limit cycle if these things are met, all right? So let me just write it out. It's kind of in more formal notation. Or I say more formal notation, I just mean let me write it out in more detail, because it's quite a powerful theorem, okay? So it's deserved of it. So in other words, this basically tells us that we need to choose a point, x, y, which is always satisfied, by what we have at the very start of all this, dx by dt equals f, and dy by dt equals g. It should be d. Okay, so same thing as before. We've got a point x, y, and that satisfies both of these. Okay, great. Okay, so in other words, we've got kind of like a trajectory, a limit cycle, right? Not a limit cycle, a trajectory. Yeah, and we've also got initial conditions. Okay, so at the birth of all this, we've got initial conditions at time 0 given by x, some value, and for y, same thing, another value. All right. Now, suppose we have a solution curve which is bounded as we go forwards in time. So we have a solution curve which is bounded. That's the crucial word. Remember, bounded is just, if you like, fencing something off. Okay, so it becomes bounded. That's not how you spell bounded. That's how you spell bonded. Bounded as we go forwards in time. So as t approaches infinity, we go forwards in time, and it basically becomes bounded. So if you like, at the start, it may just be a point, but then as we go forwards in time, it becomes built up, built up, built up, built up, built up, and then we basically form some bounded region as we go forwards in time. So if you like, we're building the fence as we go forwards in time. All right, and at the end, it becomes bounded. Okay, then we've got two cases. So either we've got two options. We've got two options. XY, so our point XY, which satisfies these equations. All right, so our point is an equilibrium point, or it tends towards an equilibrium point. So it can be an equilibrium point, or it tends to an equilibrium point. Okay, or the other option, that it tends to an equilibrium point. So our point, or a solution curve, this is our solution curve, it tends to a periodic solution. So if you're like me, whenever I see theorems like this, I sit back and I think, okay, great, that's all very well and good. What on earth is it saying? Let me try and put it in context. So that's exactly what I'm going to do. I'm just going to make this a little bit smaller, so then we can keep this in mind. Let me just make that a little bit smaller, maybe. So we can keep this in mind over in the corner. That's probably enough. Stick it over here, maybe. All right. Rubbish. Okay, that's fine. I'll just keep it like this, maybe. So you can kind of look at it as you go along. Try not to make it too small. Okay, so basically what we've got is we've got a solution curve. This is my solution curve. All right. And this is my equilibrium point, which is in the middle, or within this solution curve, essentially. So this is bounded solution curve. Okay, it bounds off this region here, and my equilibrium point lies in this solution curve. Well, it's just common sense. All right, this is just common sense. Basically, what this theorem is telling us is that either our solutions tend towards this equilibrium point. So either our solutions, this is again, it's the same solution curve which is bound. I can't draw it exactly the same. Okay, so either our solutions tend towards our equilibrium point. All right, so they all head towards our equilibrium point. So that's the first option. Either that happens. The other option which you can have is, because it's bounded, it tends towards our solution curve. Okay, so there's our solution curve. It tends towards our solution curve. Okay, so those are the two options which you can have. So it either tends towards our equilibrium point, in which case it tends towards our equilibrium point, so it tends towards our equilibrium point, or it tends towards our solution curve, and so it becomes a periodic solution. Hopefully you can see that it's going to become a periodic solution, because it's bounded. Okay, it's a bounded solution curve, so if it tends towards that, then it basically becomes a periodic solution. It gets in that cycle. So if you like, it's exactly the same as what I was talking about at the beginning. Kind of very similar to what I was talking about at the beginning, should I say. This is our sink example. Okay, so it's bounded by our sink. You can't get out of this sink, and it all falls towards our equilibrium point. So that's this case. It tends, as we go forwards in time, it tends towards our equilibrium point. And the other case is when we've got the upturned sink, all right, and it falls towards our periodic solution. So it falls towards our solution curve on the outside, which is bounding it. So it becomes a periodic solution. Okay, so that is all the Poincare-Bendixon theorem is telling us. Basically, it either tends towards this, because it's bounded. Okay, it's bounded by the solution curve. There's only two things which can happen. It can either go inwards or it goes outwards, and because it's bounded, it can't go any further. So if it goes outwards, it can't go any further than this bounded solution curve. So therefore, it must become a periodic solution. Okay. or the other case, it falls towards our equilibrium point. Those are the only two options which can happen, and the whole reason why this happens is because we've got a bounded solution curve. So it tells us that we can't go outside the solution curve. Now, the only last thing I want to do is I want to go back to this kind of idea of limit cycle. So basically, if all these kind of things are satisfied, so we've got a point xy which is satisfied by this and initial conditions, and we've then got a solution curve which is bounded, then that tells us that there has to be a limit cycle which exists. All right. So this is a really important theorem. Okay. Basically, so let me just run through that again, maybe a little bit slower. You've got a point xy, and it satisfies these system of equations. Okay, so x and y is just satisfied. So x changes over time, and y changes over time, and it satisfies these system of equations. So it's just a point which is satisfied by these equations. And you've also then got initial conditions, so you know what happens towards the beginning of time. Okay, and you've also got a solution curve which bounds off some region. It literally builds up a fence as we go forwards in time. Okay, then either our point tends towards the equilibrium point. Okay, so then it becomes an equilibrium point, or it tends towards the boundary, in which case it becomes a periodic solution. And if that's the case, then it tells us that there has to be a limit cycle which exists. All right. Now, the only last thing that I want to talk about is kind of go back to this idea of limit cycles. Okay, so go back to this idea of limit cycles and talk about their stability. Okay, now this is nice, easy kind of stuff. Now I've talked about the main meat and bones of it, or the meat and potatoes. Meat and bones, where did that come from? Meat and potatoes. I want to talk about limit cycles and their stability. So there's different types of stability. There's asymptotically stable. Asymptotically stable. This is kind of the same things as what we were doing before. Asymptotically stable, and that's basically where we've got this kind of thing going on. So it heads towards the closed trajectory. Here's the closed trajectory. It heads towards the closed trajectory from both sides, so both the inside and the outside. So we've got an equilibrium point in the middle, heads away from this equilibrium point, and it ends up on this closed trajectory from the inside, and it also comes into this equilibrium point from the outside. All right. So it heads in like that from the inside and the outside as well. So that's asymptotically stable. This is sometimes also called orbitally stable because it heads in from both sides. So this is sometimes called orbitally. It's difficult to say stable. So orbitally stable is where it comes in from both, heads towards the trajectory, closed trajectory from both sides. Okay. The next example is, or the next case of stability is semi-stable. Okay, and that's basically where it heads towards this closed trajectory from one side. So either it heads towards it from the outside, okay, so it heads towards it from the outside, but the inside heads towards the equilibrium point. All right, or it heads towards this closed trajectory from the inside, okay, and then the outside the outside heads away from it. All right. So it heads towards it. So either it heads towards it basically from one side, and we call that semi-stable. Unstable. Hopefully that should be fairly obvious. So unstable basically means it heads away from this closed trajectory from both sides. So we're talking about limit cycles now. So we're just talking about this closed trajectory. Okay, fairly obviously. And unstable is basically where it heads away from it from both sides. So the inside heads towards the equilibrium point, and the outside heads away from it. All right. Okay, and then the last case is just a stable case, and stable case we don't usually tend to talk about, but it's just basically it neither approaches nor departs. So in other words, it just kind of stays in one place. All right, just kind of stays there. So these are all the different cases. You can have asymptotically stable, or orbitally stable, the same thing, where it heads towards it from both sides. Semi-stable, where it only heads towards the closed trajectory, where it heads towards the cycle from one side. And unstable, where it heads away from it from both sides, and then just stable is just where it stays there. All right. So that's pretty much everything I want to talk about. Prong, Bendixon. I'll do examples and stuff on them, but essentially they're the main ideas. All right.